Okay, does it show recording on everyone's? Okay, great.
Yeah, it's recording.
Perfect. Okay, I'm actually gonna let Ashley start because she actually prepared a very nice presentation for everyone that explains normal distribution, which I think is an important base to explain everything else. So Ashley, if it's okay with you, you can start, and then I will go through the 3 tests that we did with Martin.
Yeah, I can start it. Well, could you see the screen? Yeah, yeah, perfect. So I will make a brief introduction about the normal distribution. I think it's the core concept of the statistics, and it's quite simple and normal. There is no formulas, no mathematics, so I think it's easy to understand. And that's it. So what is normal distribution? I think we have used these histograms, and here is the frequency of I think each variables, that's how many frequencies they have and how many numbers there. And if we put a line on it, and that could be the normal distribution. So the line here, the area, this area could be a percentage. And here, this graph is about the normal distribution. You don't need to understand what really the formula is, but from a really difficult theory, mathematicians can demonstrate that most variables distribution belong to this normal distribution. So you can use this distribution to estimate variable models. And that's why SPSS use this model to examine what we want and what hypothesis we have. And here, but we need to understand what is confidence interval, right? Yeah, here is this. It's really hard to understand, but here's a really simple example here. Okay, so I want to know the mean of people's height, but the population on the Earth is over about 7.8 billion. So maybe only God knows the exact number. And I decided to sample some lucky people and calculate their average height. But so if God told me the mean height is about 150 centimeter, then the normal distribution curve is like this. And know the mu, this one is the mean number of the height. And this curve would seem like this. And I sample about 10 people, and the result could be found on this graph. No, so we got these data, and then we just calculate the average, and we got this point. But we only have 10 people to estimate the mean, and it's not concluding the final answer. Yeah, it's 145, right? So how could we make it more credible? Then we smart people, think a really clever idea is that we make an artificial interval. Just at this point is we got the sampling mean, and we made an artificial interval, this green line, to cover more data. So you can see the mu, the real mean, 145 centimeter, will be covered in this interval. So if the confidence interval is 95%, it means that the probability that your interval covers the real mean is 95%. So if there are about 100 intervals, 95 of them cover the real mean. So it looks quite credible than we use just one single point here. But there is about 5% that you may not cover the real mean. Just look at this point. If you build this interval, but you don't cover the 145 centimeter here. And because there is the idea of low probability events and the hypothesis testing, the low probability events means that the probability is less than 5%. So we always use 95% to examine some hypothesis. If you test your original hypothesis and it is less than 5%, it means that you should reject your null hypothesis and accept the alternative hypothesis. So the word reject means that it cannot happen for the low probability. And the alternative hypothesis H1 is what you want, just like Martin have said in his PowerPoint. And so when SPS shows the significance is lower than 0.05, then you will get your answer. It means that what you test, what you want, what your hypothesis is right. And that's my introduction about normal distribution. And hopefully it will be understandable.
Just for everyone, I know we didn't take hypotheses with Martin's class. We didn't do H null and then our hypothesis. So I'm going to explain this right now for everyone so that you don't get confused, especially since Ashley brought it up. So this was just kind of like an overall to understand what normal distribution is and why we have the 68% and the 95%, and what do those actually mean. So 1 second, let me just charge my laptop. Okay, so I actually did SPSS in my undergrad, and I was able to find the files from my undergrad course, which go through each test separately. So I have the chi-square and the t-test and another test that we didn't do yet. And I thought that it explained it very well, much more detailed than what we took with Martin. So I'm going to share that for everyone right now. I'm going to share the slides and I'm going to go through it to explain what each test is, what does it mean, why we do it, and what are the kind of results that we can get when we're doing those different tests. And please feel free to stop me at any point if you feel like this is something you don't understand. And I will try to go through it as best as I can. Okay. Okay. So the first test that we went through with Martin was the chi-square test. If you guys, by the way, if you like these slides, I can share them with everyone on the group later on. So let me know if you find that these are helpful, and so that I can share them with you guys so that you can take a look at them later. Okay, so this is just a table that explains the different tests and what kind of variables you need to have. Discrete and continuous are just different words for nominal and ordinal and scale. So discrete is nominal or ordinal, and then continuous is scale. So for a chi-square test, we need both variables, the independent variable and the dependent variable, to be nominal or ordinal. So does everyone remember what independent and dependent variables are? If anyone wants me to go through it, say something so I know to go through it again. Okay. Okay, so we need both variables to be, so a chi-square basically doesn't work if any of your variables are a scale. And that's why you would end up doing a t-test for them. Okay, so the type of statistics you use, which is the type of test you use, depends on these three things: the number of variables analyzed, the level of measurement, and the research question. So I think someone said in the CCNPR, it depends. In the CCNPR group on Instagram, someone posted, it depends, Tony Bing. That's literally what this tells you. What kind of test you use depends on what you're looking to find. Okay, so this just goes through the discrete and the continuous. So as you guys can see, discrete is nominal or ordinal, and continuous is scale. Okay, so the chi-square analysis. Don't read through all of these. Some of them are useless, but the point is, it's also called a test of independence. So the point of a chi-square test is to tell us if the two variables are dependent on each other, if there's an association between both variables or if they're completely dependent. Okay, and it measures the difference among groups. These are examples of different types of chi-square tests. So there can be a 2 by 2. An example is gender by political party. So you have Republicans, and sorry, I'm doing American because I don't know the British. I know the American better. So you have Republicans and Democrats, and then you want to see the gender, male and female, for each Democratic party, political party. So you do a chi-square test to test that. And a 2 by 3 means that one of your variables isn't just 2, it's 3, so high, medium, low. So an example would be gender by dosage. So the dosage is divided into 3 and not just 2. So it would also be the case if political parties are more than just 2, if, I don't know, Democrats, Republicans, and Independents, I guess, that would also work for a 2 by 3. Okay, so we're interested in the relationship between 2 discrete variables. One of them is in the row and one of them is in the column. That's how the table is going to be when SPSS puts it out for us. Okay, so I'll go through these later. Okay, so this is to explain what a null hypothesis and what an alternative hypothesis are. So I don't think we need these for now for our assignment for this class, but you're going to need them for your dissertation. You're going to have hypotheses for sure. So basically, the hypothesis that you have is usually HA, the alternative hypothesis, which states generally, because what you're going to want to prove in your dissertation is that there is a relationship between the variables. So you would have an alternative hypothesis. And you always need to have a null hypothesis because there's always the chance that you're not going to be able to prove your own hypothesis. The way it works in statistics is you always need to disprove the null hypothesis to prove yours. So if my dissertation is on, I don't know, I think that more women are Democrats than men. Okay, what I need to prove is not that, I need to prove the opposite of it, which would be the null hypothesis. I think there's an example. I'm not sure. Okay, yeah, so this is the example we're gonna look at, and it shows the hypothesis and the null hypothesis. So the research question would be, this has nothing to do with the example I just gave you, forget it. So we're gonna look at this. The research question is, do those who eat ice cream tend to eat chocolate bars as well? So our 2 variables would be person who eats ice cream and then person who eats chocolate bars. My hypothesis, the one that I have, is those who eat ice cream are more likely than others to eat chocolate bars. Okay, that's what I want to prove in this research that I'm conducting. My null hypothesis is that there's no relation between eating ice cream and eating chocolate bars. So in order to prove my hypothesis, what I need to do is prove the null hypothesis wrong. I need to reject the null hypothesis to be able to say that, okay, my hypothesis is right. I need to prove that there is actually a relation between eating ice cream and eating chocolate bars. Is everyone still with me? Okay. So, okay, these are just the data. Person 1, yes and no. Person 1 doesn't eat ice cream, but eats chocolate. Person 2 eats both, etc. This is just the data set that we have. And then this is the frequency for each. So this is, here we're kind of getting into what Martin, the example that we started with Martin. I'm just giving you this example instead of Martin's because it might clear things up. We'll do both actually. I think the more examples we do, the more you guys will understand. Okay, so the frequency for ice cream, people who eat ice cream, that's 11. How do I get the, I want the small spotlight thing. Okay, yeah. So the people who eat ice cream are 11. And then the people who don't eat ice cream are 9. And then here we have the same for chocolate, 12 eat chocolate and 8 don't. And these are the respective percentages for each. Total 20 for each, and then total 100%. Okay. Oh. Shoot, I hate this. Okay, sorry. Okay, so let's forget this. I'm not going to go through the math, by the way. I think it's going to just complicate it for everyone. So I'm not going to go through this where it's going to compute the frequencies. I'm just going to give you guys the actual frequency that we're going to get. No need to complicate your lives, because you don't need to know that, since SPSS is going to do it on their own, on its own, and just give you the result. If anyone's interested in understanding the math, we can do that some other time. Okay, so is it just in percentages? Okay, it's fine. So this is how it's gonna end up being. So we have the ice cream in the rows, and then the chocolate in the columns. And so ice cream 1 and chocolate 1. Let me try to find. Hang on, let me do the spotlight again. Okay. Oh, yay! Excellent. So this means people who eat ice cream and eat chocolate, right? That's 7 people. That's 35%. Chocolate 1 and ice cream 2 means people who eat chocolate but don't eat ice cream. That's these guys. And then here we have people who eat ice cream but don't eat chocolate. And here we have people who don't eat ice cream and who don't eat chocolate. So this is what the table tells us. Does everyone get that? Okay, great. Hang on, how do I erase everything? Okay. So this is a different way of putting the data set. Oh, right, I have to explain expected value and, right, or not? 1 second. Sorry, guys. Am I still sharing my screen? Can you guys see my files?
Yeah.
Okay.
You can see the PDF.
Oh, you can see the PDF still? That's it?
Yeah, that's all.
Okay, that's really good. That's fine. Better for me because I can go through different things. I'm just trying to remember which one had the expected value that I needed to go through. Okay, yeah, so it is this one, the expected count. Okay, so I'm gonna explain that quickly. I'm not gonna go through the math of it again, because it's too complicated, but basically for a chi-square, you need to always compare what you have, the data you get, with the expected number that you're supposed to get. The expected number is calculated by SPSS, and there's a mathematical equation for it. Again, I'm not going to do it because it's just going to complicate it for you guys, but just know that it is based on actual concrete stuff. It's not just, it doesn't come out of the blue. And what Martin said before is that in a table, the expected count should be above 1 for all cells and should be above 5 for more than 80%. So in our table, we can see that all of them are above 1, right? But 2 of them aren't above 5, right? The 3.6 and then the 4.4. So usually we have to fix this red flag. So again, this is not needed for our assignment, I think, because I highly doubt that they're going to give us a table that needs fixing, because he said several times we're not going to need to do anything on SPSS. So we're just going to have, I didn't look at the assignment. I haven't looked through it, but I'm pretty sure that the table they give us is going to be the final one that doesn't need any amendment. But usually for later on in your dissertation, if you're doing a chi-square, you need to make sure that these two things exist, that your expected count for all cells is above than 1, and then more than 80% of them are above 5. If they're not, you need to fix that. And you'd have to recode the variable and sum up some categories together to make sure that everything's above 1 and that 80% are above 5.
I think I can explain it in a more simple way.
Go ahead.
So if you want to understand the expected value, it looks like if you do an experiment and you run it many times, then the expected value could be the whole times you have done, and you calculate the mean value of each experiment. So it's an average value. And that is what we expect it could happen. And about the 5%, I have mentioned that if the probability is less than 5%, it means that this event could hardly happen. So if your expected value is less than 5, it means that this event could not happen in the real. So you need to add this value into your last option to calculate them together. Does that make sense?
Yeah, it made sense to me. Does anyone want me to go over that? So basically, why it needs to be over 5 is that if it doesn't reach your 95% confidentiality level, it means that it's highly unlikely to happen. So there's no point in even, getting the results from the table if more than 80% of your cells are less than 5. So you need to make sure that they're above 5 in order to have a higher likely probability of your results actually being reliable. Yes or no?
So when we look at this table, we need to compare the O and E columns.
Yes.
Yeah.
You don't need to compare them. Right now, you don't need to compare them. Really, to make sure that your test is reliable, all of your E's need to be above 1, which they are. But other than that, 80% of them need to be above 5, which it's not.
Okay.
Okay, now, for some reason in my undergrad, apparently we didn't care about that. And you guys are going to see that we're going to go through this table and we're going to continue and we're going to test it as if nothing's wrong. But Martin said that it is important that 80% of your expected values are above 5. So just keep that in mind for later on, because in case you don't reach that requirement, you're going to have to recode your variables in order to reach that requirement. Okay. Yeah, so first of all, that's our chi-square. It's 0.134. Okay, it's this one, the x squared, the nice red one. So we need to actually look at what that means. We need something called our degree of freedom, which means the number of scores that are free to vary. As Martin explained it, it's how many variables are free, literally just free to go up and down. This is very simple math. It's just number of rows minus 1 times number of columns minus 1. And in our case, it's 1 because we just have 2 columns and 2 rows. So this is 2 columns, 2 minus 1, 1, and then 2 rows, 2 minus 1, 1. So 1 times 1 is 1. So our degree of freedom is 1. So our results for now is that our chi-square is 0.134 and our degree of freedom is 1. Now, what do we do with this information? What does this tell us? To check it, we need to look at this table. So I think this table is usually, they don't give it to us. Martin didn't give it to us in class, but you can find it online. But if I send you guys this, then you guys have it in this slide. And this is the table that kind of explains what it means. So we have a degree of freedom of 1, right? and our chi-square is 0.134. So we start looking to see, oh, wait, hang on. Oh, yeah, okay. So we're looking to see that our equivalence, we need to have it to be less than 0.05, which goes after what Ashley said about the 95%. And if it's above 95%, then it's a highly unlikely thing to happen. So that's why Martin, I asked again, why in class, I asked Martin, why does it have to be 0.05? And he said, anything above means that it's highly unlikely to happen. And then you can theoretically use the 0.01 and 0.001, but these are if you're looking at a research where you want to prove like to a very, very, very certain extent. Martin said that for our case, a 0.05 is enough to say that to a certain degree, we think that this is true. Okay, so we look at this at the 0.05 with the degree of freedom 1, and it shows us that the chi-square value should be 3.84. So ours is 0.134, right? So what this tells us is that our test is insignificant, because for it to be significant, it would have to be 3.84 or above. And our chi is 0.134, which is very, very small compared to what we're supposed to be getting. And what that translates to is there's absolutely no relation between people who eat ice cream and people who eat chocolate bars. Okay, so we failed to reject the null hypothesis, which is here. This is the first thing that you would need to write in your paper. Our chi-square turned out to be not significant. We failed to reject the hypothesis, and that means that there's no relation between people who eat chocolate bars and people who eat ice cream. Does that make sense to everyone? Do you need me to go through one thing before I move on to Martin's example, before I move on to how it's done on SPSS?
Yeah, is it possible to just go back over the explanation one more time, please?
Of course. Okay, so SPSS is going to do all of this for you guys. It's going to tell you, it's going to compute all the frequencies for you. It's going to compute the observed frequency and the expected frequency, which are these. Again, so there's the part of it being above 5, but I'm not going to go through that again. It's fine. So you have your expected frequency and you have your observed frequency. And after doing all of that, SPSS is also going to compute the value of the chi-square for you, which for our example ended up being 0.134. Okay, so when we have that, we also need to calculate the degree of freedom in order to translate what this chi-square means. So the degree of freedom, it's a very simple mathematical equation. It's number of rows minus 1 times number of columns minus 1. So in our case, because we had 2 columns and 2 rows, our degree of freedom ends up being 1. So the results that we need to look at in order to interpret this table are our chi-square and our degree of freedom, which are 0.134 and 1. When we have those two, we need to look at this table. Okay, so this table usually, if you have depending on each degree of freedom, you need to look at a different row. But because ours is the degree of freedom of 1, we just look at the first row. And usually, so in research, you'd want to look at the 0.05 to test if your if your test is significant or not. And as you guys can tell here, anyways, it says non-significant and significant. So if this is confusing for you, you can just try to find your chi-square in this table. So I'm going to do that just to give you guys an example. Our degree of freedom is 1 and our chi-square is 0.134. So our result would be here. Under 0.7. That's where our result would be. And if you look at the table, that means it's not significant, right? So that's one way of doing it. The other way of doing it is looking at this, which is 0.05. If you want to prove that your test is significant, your chi-square needs to be 3.84 or above. And since ours is lower than 3.84, it means that our test is insignificant and that there's no relationship between our two variables, which for us were people who eat ice cream and people who eat chocolate bars.
If the table is too hard to understand, I think I can show a graph to explain this table.
Yeah, hang on, let me stop sharing so that you can do it.
Yeah. Yeah, it's a slide from my statistics class. And actually a chi-square is also a wave, but it's not like the normal distribution wave, but the reason here is the same. So if you got the numbers 0.134, right? And here you got the line here. It may lie on this, like this. You can get the number here, the 1.696, and your number 0.134 was just near the 0 point. So you can see the area here, maybe in the chi-square is about 70%. And so it means that this covers this area, but not lie on this area. And if your numbers lie on this area, it means that it's significant. But this area means it's non-significant. I think it could make sense here.
Did everyone understand? Did that make it easier to understand?
Can I just ask? So, oh Christ. So if the 95%, that's saying that if you're within that 95, can we share that graph again, please? Because I was understanding it for like 2 seconds. Thank you. So the 95%, if you're in that bit, that means that your expected and observed are related?
No.
It means that
it's not your expected and observed that are related. It's your independent and dependent variables, which are chocolate eating and ice cream eating.
Okay.
So the expected and the observed aren't really related. You don't really need to look at them together. You only need to look at the expected value to make sure that you can run your test. That's it. Other than that, you don't really need to look at the expected value.
The expected value is only used for calculate the chi value. So you don't really need to understand what is used for. You just need to understand it's just used for the calculation here.
Okay. I feel like I'm almost there.
It's fine. We're gonna go through Martin's example now. Hopefully that will get you all the way there.
Yeah, maybe that'll help. Okay.
Yeah.
Thank you.
I'm gonna share my screen again and go to Martin's presentation. Okay, so I'm not gonna explain these again. I'm just gonna look at the example and go from there. Okay, this is the one that says that, okay, this is a red flag. Okay, let me try to zoom in so we can see the input. Okay, so in this case, in Martin's case, I think we were calculating how many times you go to the store, and if that's related to whether or not you're Asian or non-Asian. So we wanted to see the association between the frequency of shopping, and your nationality. So in our row, we had, so first of all, these are both nominal / ordinal, they're both ordinal variables. So that's why we did the chi-test, the chi-square test. And above and beyond, we want to see if they're associated or not, right? So that's why we're doing this test. So the first table that SPSS is going to show you is this. So let me get the, where's the little thing again? Okay, so I'm going to go through them just to tell you guys what all of these mean. So this 21 here means that, so here we have our Asians equals 1 and rest equals 2. So these are these two. So these are Asians and these are non-Asians. So 21 Asians go to the supermarket. Shit, Martin removed the labels. I think it was 21 go, shit, sorry, I'm gonna have to look at the other slide. Once a week, okay. So 21 Asians go once a week, whereas 15 non-Asians go once a week. But it might be smarter to look at the percentages, because 21 might be a bigger number than 15, but compared to the total, 15 is more than the half of the non-Asians, whereas 21 is only 30% of the Asians. So I'm going to go with the percentages. So here we have 30% of Asians who go once a week versus 50% who go once a week. And then 2 to 3 times a week, 53% of Asians go that many times, 48% of non-Asians, and etc. That's what these tables show you. And then here we have 0. 0 non-Asians go all the other times, 46 times or daily. Okay, so that's our first table. It's just very basic frequency for each demographic. Does everyone get this part of the table? Okay, perfect. So now the chi-square result. Okay, is this our, oh, this is our chi-square. Okay, so our degree of freedom is 2. And that's because, so in the rows, we have 2. So 2 minus 1 is 1. But our columns, we have 3. So 3 minus 1 is 2. So 2 times 1 is 2. So in this case, our degree of freedom is 2. Okay? So that's what it tells us. It tells us here that the degree of freedom is 2 and that our chi-square is 0.027. Okay, so I'm going to go to our table again. Oh, I don't know if you guys are going to be able to see it. Can you guys see my table, or can you guys see still the Martin's PDF?
We can still just see the table from Martin.
Okay. That's fine. I think anyways, actually SPSS makes it even easier for you guys, where you don't even need to look at the table, because this number, this 0.027, is actually the number you would get in the table, is actually the number that needs to be less than 0.05. So I think it's the probability. Ashley, can you say if I'm correct or not?
So the chi-value, the Pearson chi-square is a test method of chi-square test, and the value, the 7.2 and 50. This value is a chi-square value.
Okay. And
this significance is when you use this chi-value into that table that Yari have shown that's a really hard reading table, and then you got this value on the chi-square on that graph. You got the percentage here. So you combine this percentage into 0.5. Okay. 0.05, yeah. So it's about 2.7% versus 5%.
Okay.
So
Okay,
it's
I see.
lower than 5%.
Okay, so
Then it could
in-
be significant.
okay, so in Martin's thing, the 7.255, that's the one we have to compare to our table. So here in the table that we see, we have the degree of freedom, it would be the second one, the second row. If you go to 0.05, you need 5.99 or above for it to be significant. And because we have a 7 point something, that will mean it is significant because it's above 5.99. But you don't necessarily need to do that because the percentage that we have there in Martin's table, this one, the 0.027, you can just compare this to the 0.05. So if it's smaller than 0.05, then you're good. And that means that your test is significant.
Okay, so we don't actually need to look at that table.
No,
that other
you
table.
don't need to look at
you
the
have to
table.
Google.
Mm.
Okay, so long as that number on the
Yeah,
Pearson chi-square row, say,
Yeah.
is less than 0.5. 0.05?
yeah, 0.05.
Okay, great.
Okay, so because ours is, it means that our test was significant and that there is a significant relationship between being Asian and going to the grocery store. Does everyone get that?
Sorry, what was that last sentence you said? I was writing notes.
Oh yeah, no, I just said that because our test is significant, that would mean that there is a significant relationship between being Asian and your shopping frequency. Okay, and I'm gonna go to the next slide because I think it oh, clear all drawings. Okay, I think it shows us the interpretation. Oh, okay, right. There's still this part, but I'm just going to show you guys before I do Kramer's V, how it would have what you have to type would look like. Just that one sentence that's significant for us. This is it. Overall, these differences result in a significant association between the place of birth and the shopping frequency. And then you always have to write it this way. You have to include your chi-square, and you have to include the probability that you compared your chi-square to. But I mean, we have these. So while writing the SPSS assignment, you can just look back at this paragraph to kind of know what results you need to include and what results you don't need to include. Now, before I explain Kramer's V, does everyone understand how we figure out if the test is significant or not by using chi-square? Okay, great. Okay, so actually my other slide explains Kramer's V a bit better because it shows how you figure out if it's a small effect or a medium or a high effect. So let me share that. Okay. We need Kramer's V to be able to say how high or low the association is between our two variables. So we were able to say that, okay, being Asian and going to the store are related, but how related are they? How high is this association between our variables? We do Kramer's V to figure out, so we don't do anything. SPSS gives us Kramer's V value that would be able to tell us how significant it is. And so Martin didn't give us this table, but I thought it was interesting because with him, he just said, oh, Kramer's V is low. The association is low. This explains why. So for each degree of freedom, there's a different number that needs to be met in order to tell if it's a small effect or a medium effect or a large effect. So once you get your Kramer's V, you just check where it is on this table and you figure out if it's a small effect, a medium effect, or a large effect. So in Martin's example, our Kramer's V was 0.272. Okay, and we have a degree of freedom of 2. So that would mean that our Kramer's V lies in between the medium effect and the large effect. Oh wait, hang on. Yeah, no, 0.272. That's the value that we got. Sorry, let me go back to the other one. Oh, so you guys are seeing the same one. Okay, so that would mean that it would probably be a medium effect, right? Because it's 0.21 and ours is 0.272. So you would just add that in your analysis at the end. You would say this association is of low strength. So I don't know why Martin said it's low strength, because my table says it should be medium strength.
Where does the 0.272 come from?
It's you also get it from SPSS. Hang on, I'm gonna stop sharing so I can share the other again. So on SPSS, we'll go through SPSS and where you get these values, but there's another table that you just take some stuff in while doing the analysis that you want, and then you get the Kramer's V in one of the tables, and this is what you get. You get the annotation tool. This is it, Kramer's V. Okay, so it's 0.272, and you need to include that in your interpretation, because it just tells you if it's how strong the association is. So again, I don't know why Martin put that the association is low when my table showed that it's medium. Ashley, do you have any clue?
I think he doesn't consider the degree of freedom, just compare this value between 0 and 1. For normally we just consider the Kramer's V between 0 and 1, and if it's a small number, then we think the strength of association is low.
Oh, okay. Okay, then you guys can do what Ashley just said. Just go between 0 and 1 and forget the table that I showed you guys. Does everyone understand what Kramer's V does and how you need to include it in the results?
I do, but just to check, is it so like if we're trying to figure out what it is it that all we need to do is just look on the table to see where it would fall?
Yeah, well, actually, don't even look at the table. Follow what Ashley said and figure out where it goes between 0 and 1. So if it's towards 0, then it's low. If it's towards 0.5, then it's medium. And if it's toward 1, then it's high.
Okay. Okay.
Ethan, you wanted to say something?
I was just going to ask the same thing. So it's okay.
Oh, okay. Okay, great.
Thank you.
Okay, do you guys want me to go through how you get all of this through SPSS or not?
Do we need to?
We don't need to. That's why I'm asking you guys, because we don't need any of that for the assignment. You just need it for the dissertation. But to be honest, Martin in his slides always explains how you can get each table. I mean, he says what you need to click on SPSS to get there. So we don't need to go through them. My main thing right now is to make sure that you guys understand the test and understand how to interpret them. But if anyone's interested, I can go through it quickly.
Obviously, other people might have different opinions. I don't really want to, because I think even if I learn how to do it now, I'm going to forget how to do it by next June. So I don't want to waste anyone's time. Okay, if anyone wants to go through SPSS, just unmute yourself and say yes. If not, I'm going to assume that no one wants to go through it, and I'm going to go to the second test. Great. No one cares about SPSS. Poor Martin. Oh, but I do think we need to know how to do it for the assignment for this seminar, though.
Yeah,
I'm not sure. Sorry, Ashley, what?
Yeah, I think for the tomorrow seminar, we need to use the SPS to calculate these cross tables.
Okay. So should I go through it, guys?
You might as well.
Yeah. I can't say I was listening very closely on Monday, so I think it's probably for the best.
Okay, yeah, it's fine. It's relatively easy. It's not the hard part of today. So if you understood what the test stands for, figuring like understanding how you do it on SPSS shouldn't be too hard. So let me just open the data that we need. So that's
Is
gonna
it the
take a while
same?
because I haven't opened SPSS today.
Yeah. Is it the same data we worked on last seminar?
Yeah. No.
Yeah.
No, I'm not. I'm not gonna go through the seminar data. I'm gonna go through the lecture data.
Okay.
They're-
Have you given
they're
us
different.
that data? Are they?
Yeah.
I thought we were like slowly working on a single set of data over the weeks.
No, in the seminar we're doing one thing, and then in the lecture we're doing another thing.
Hell.
I'm amazed that you
Where do I
didn't
get
notice.
the data? I didn't. Like, that's probably why I've been so confused.
Okay. I opened the wrong data set. That's great. If anyone has SPSS downloaded and would like to open the data set, you guys can do that so we can go through it.
Yeah, I think I can show my screen.
Oh yeah, go ahead if mine still hasn't
Yeah.
opened, so go ahead. Let me stop sharing 1 sec. Okay.
Yeah. Okay, let me see. This one, right? This
Yeah,
one's
just
for
check if there's Asian at the end, then that should be it.
Oh, I don't think. Just wait a minute. I think I need to open a new one.
Okay, look at both of us opening new ones and not working.
Yeah, this one. Yeah, this one.
Oh, okay, okay.
Yeah, could you see that? Oh, just wait a minute.
Mine opened if you want, and I have the Asian at the end, so I can.
Yeah, could you see that?
Oh yeah, now we can see. Yeah.
And so, what is the?
Wrong one. Wait.
What do we want to test? I forgot. Let me see. Yeah, the frequency.
Yeah.
So if you want to test the frequency and the relationship with agent, you need to use this analyze descriptive statistics and this and cross tabs. And here the row is your independence and the column is your dependence. So you want to analyze with agent and non-agent, so it should be on the columns. And the frequency should be on the rows. Sorry, where's the frequency? Oh, I think it's this one, right? Q1, half, yeah. And you got these statistics. Here you should click the chi-square. And you want to get the value of primal V, so you also need to click this. And then click continue. And the cells, if you want to see the percentage of your rows for the frequency of your to the store, you need to click the row here, the percentage row. Then you click continue, and then so you will get a table of Asian, non-Asian. And here is about once a week, 2 to 3 times a week, and 4 to 6 times a week. And then you will get a chi-square test result here.
Oh, but wait, yours is different.
Oh, I remember Marty have.
Did you use the recoded question?
Oh, I think I didn't
The
use the
recoded
recorded
value of the other one.
Yeah. Oh, I think he had added these times into.
Yeah, that's what I mean when he recoded and added those together.
So to the cross tabs, I see. It's this one, yeah. Recording, yeah. And here all the same.
Yeah.
Then you will get the number here.
Yeah,
Yeah,
there
it's
we go.
it's 0.027 here. Yeah.
Did everyone get how to do that?
Do I need to do it again?
I'm just catching up because I was being so slow. My computer.
Would you like Ashley to go through it again?
I think I'll be okay. Just hang on. Look,
It's fine. I think I could see it again. So you need to use the descriptive statistics and cross tabs, and you put the recording question 1 into the rows, and the Asian and non-Asian into columns, and then you click statistics and click the chi-square and phi and comma v, and continue. And in the cells, you click the percentage, the row, and continue, and then click OK. And you can get the answer. And you just need to see, you just need to use the value, the chi value into your final interpret. The chi value is 7.255, and the degree of freedom is 2, and your significance is 0.027. You just need these 3 numbers. And here is the symmetric measures, and you need to cross this value, the 0.272. You just need these 2 numbers to finish your interpret.
Okay.
Does that make sense?
Yeah.
Ethan, you still look lost.
Who?
You.
Oh yeah. Like, sorry, it's just my my computer's being so slow because I'm trying to do it at the same time as being on Zoom.
Okay, it's fine. We'll wait for you to make sure you get it before we move on.
Well, the thing is, I downloaded the data set that was in the lecture thing.
Yeah.
And it doesn't have Asians, non-Asians.
Yeah, you need to record these variables.
Yeah, but like it was there on my other one I did last week. But like I've downloaded the one that he worked on this week. It's not in it. I don't know if I've just got the wrong one.
I'm using the one I have saved from like 2 weeks ago, so I'm not sure about his.
Right. I'll just try it on my own because it was actually good. Here we go. So analyze, descriptive statistics, cross tabs. In the rows, I have.
You can put whichever one you want.
Yeah. Oh, fucking hell, that's the wrong one. I see what you mean. Yeah, they are different. Oh crap! Right, just carry on. I've accidentally closed SPSS now, so I'm just ruining everyone's fun. So.
Okay. Anyways, if you go through it later today and you're not sure how to do it, just text me.
All right. Thank you very much.
Of course.
I'm sorry for the hassle.
A quick question to buy Ethan some time. So the Kramer V value
what it's basically saying in this exercise is that in general, there is a relation between whether you're Asian or not and how many times you buy at the supermarket. But then the Kramer value, what it's telling you, it's that while there is a correlation, it's a very low
Yes.
relation.
Yes,
Okay.
exactly.
Okay, perfect. Thank you, guys.
Of course. Okay. If everyone's on board, we're gonna move on to the t-test now. Okay. Oh, I didn't even notice Kier was here. I just saw the chat and he said that he left and I didn't even see his screen at any point. Whoops, okay. Okay, let me share my screen. Okay. So the t-test, so to be able to conduct it, you need one of your variables has to be a scale and the other has to be nominal or ordinal. So there are different types of t-tests. There's a one sample t-test, a two sample t-test, and in the two sample t-test, there's an independent sample and a paired sample. I will explain the difference. First of all, one sample t-test, Martin said that we don't really use it. He said that even if you can do a one sample t-test, a two sample t-test works as well. So we tend to always do a two sample t-test. The difference really between the one sample and the two sample is that on your normal distribution, the one sample t-test kind of tests only one side of the curve, whereas the two sample covers both sides of the curve. So generally, you would do a one sample t-test if you know what side of the curve you expect your results to be in. But when you don't know, you just do the two sample and then you figure it out. But generally, the two test just works for everything. Okay, now the difference between an independent sample and a paired sample. The independent sample is when you test samples that were drawn randomly from different populations. So like what we have right now, like the example that we're doing with the online shopping and I don't know what. It's the same test, but different people. Same variables, different people. In a paired sample, you're testing the same variables, you're testing different variables, but the same people. So if you're doing a test over a long period of time, you would use a paired sample. So if you're testing, I don't know, consumption of pretzels, I just bought pretzels and they're right in front of my face. So if you're testing the consumption of pretzels between people who are aged 18 to 25, and then those same people when they're 30 to 35, that would be a paired sample because it's the same respondents, just different observation. Does everyone get that? I think my slide explains it better. Hang on, let me open it. My computer just froze, 1 second. Okay, yeah, hang on. I have examples here. Let me stop sharing and then start sharing. Okay. So independent sample t-test means of two different groups. So gender, an example would be gender and posting on social media. So the difference between males and females when it comes to posting on social media. As you guys can tell, this is very similar to the chi-square. The only real difference is that one of the variables is scale. Both of them aren't nominal / ordinal. So the paired sample t-test is means of the same group at 2 different points in time. So an example would be starting salaries and current salaries of managers. So does everyone get the difference? No, yes?
Could you go over it one more time, please?
Same.
Yes, yes, of course. So in the independent sample, you're going through, it's the same period of time really. So an example would be you have males and females and you want to see whether or not that's related to their posting on social media. So you're testing 2 different groups, male and female, on one variable compared to one variable. In the paired sample t-test, your variable is the same group. So it's not male and female, it's the same group, but over a different period of time. So the example here is one variable is salaries, the other is current salary and starting salary. So it's the same group, which is managers, but you're testing their starting salary and their current salary. But the group is the same, it's managers. It's not like managers and, I don't know, executives, and you're comparing their salaries. You're comparing the salaries of the one group, but at different points of time. Okay, great.
So one of them tests 2 different groups, like men versus women.
Yeah.
And then the other one tests the same group.
Yeah.
Like you said, the example is like managers. They test the same group, but the sample you said is different?
Not the sample, the other variable is different. It's because the way it's done is it's not at the same period of time.
Okay.
So you're the same group. So in our other case, the genders were different, and then there was posting on social media. In this case, the gender is kind of replaced by managers. It's the same group. There's no difference. The difference is in the salaries. So it's the same group, but you're testing their salary, I don't know, 10 years ago and their salary now.
Okay. So for the managers, so for all of the managers, you're comparing what their salaries were versus what their salary is now.
Yes.
Okay. So one is just that you're doing it over a different period of time.
Yeah, with the same people.
Same people, but different time periods.
Yeah.
And the other one is
not the
different
same
group,
people. Yeah.
not right, but the same
I think if you use example, sorry.
Go ahead.
So I think use the example of Marty have gave us for the closing for a seminar we need to do. So there is a group of people and you want to test the frequency of they go to these clothing shops. Then you want to examine the gender that whether influence the frequency or whether or not, then you will use the chi-square test. But if you want to know, there's a lot of clothing stores and like the H&M and Zara, and you want to know this group of people, how they think of H&M and Zara, and if there is any difference between what they think of H&M and Zara, and then you will use the t-test.
Yeah, but it's but it's the difference between the t-test because there's independent sample and paired sample. But I actually don't remember if Martin gave an example. Both.
I don't think he
did.
It's like sounds very foreignish to me. Okay.
I'm trying to. I'm just checking his PowerPoint. So we did the one sample t-test.
I think
and we did the paired sample.
Example of the independent samples.
Oh, he gave examples for both. He gave example for independent and for paired. Yeah, okay, so for the independent sample, Martin's example was female and male, so two different genders. And we were testing their attitude towards online grocery shopping. So very similar to the social media posting, you have male and female, and you're testing their attitude towards something. So that's an independent sample t-test. In the paired sample, his example was, do consumers consider price discounts more important than a low price in general for online shopping? Geez, that's a very complicated question. I didn't even get it.
The one that you have on your slide, Yara, I think it's simpler and it explains better because I'm reading it over now.
Yeah.
I'm getting it as opposed to Martin's. I think I'll just work with your explanation to
Yeah, okay.
keep
We'll do both. We'll do both anyways. But yeah, I will have to see if Ashley understood Martin's example because I didn't really get it. So let's, if everyone kind of understands this for now, we will go through the examples. Maybe that will make it clearer for everyone. Okay. Okay, so this just explains what the t-test allows us to do. And it basically, with the t-test, we see the difference compared to the mean. So that's why normal distribution is so important. Martin said that the first thing you need to do when doing a t-test is making sure that you have a normal distribution. And at the time I asked him, what is normal distribution? But now we know. So for the t-test, your variables need to be distributed in that normal bell-shaped. If they're not, then it just doesn't work. Because the whole point is that we're comparing to the mean, to the middle of that normal distribution curve. Okay. Did some error, we'll expect to have different means even if groups come from the same. Okay, whatever. Oh yeah, I think that was important. Yeah, so let's go through the example first. We want to know if husbands and wives drink coffee differently. So this is an independent t-test, okay? We have the hypotheses again. I'm not gonna go through them. They're just gonna complicate everything for everyone. We just wanna know if husbands and wives drink coffee differently. Our variables, the independent variable is husbands, wives, and the dependent variable is coffee drinking. So we need to check that there's a normal distribution. So Martin, when he was explaining to us how we check, he didn't do this. So you guys don't need to do this. He just said that just have it charted on SPSS as a histogram with the curve. And if it looks like a normal distribution curve, then just say, great, it looks good, so we can continue with the test. But there are actually numbers that can show you if it's normal distribution, but we don't have to worry about that, he says. Okay, so now this is the output that you would usually get if you're doing a t-test. One of the most important things in a t-test is Levine's test. And I swear to God, Casper and I were texting for like 2 hours after the course, trying to figure out what this means and trying to understand this. We got there eventually. But so basically what the Levine test is it checks that the mean for both of your genders are equally varied. So let me see, I think I have it here somewhere. I don't have the mean of each. Okay, yes, I do. So you guys can see here the mean for the for one of the genders is 7.12, and the mean for the other is 5.52. Okay, and then we have the standard deviation, which is important for us. So what we need to make sure of is that the way our variables are distributed for each gender are equally distributed. So let's say, let me see if I can draw something here. Hang on. How do I get a whiteboard? Does anyone know? Okay, it's fine. I'll try to do it here. So let's say we have this, and no, that's wrong. We have this, and we have our curve. Okay, sorry, it looks like shit. And then let's say our gender, you know, these are some variables, and then these are some variables, and then these are some variables. Okay, we want both genders to have a similar distribution of the variables. Okay, and that's what Levine's test tests. Does that make sense?
Or maybe
No?
I could explain.
Yeah, try, go ahead.
So, I will try. So the Levine test, I think Martin have explained the variance to us. Do you remember that variance? So the variance, actually the chi-square is also used the variance to test their significance. And the variance means, here is the Bell wave, and it's kind of hard to explain. And you know, the center is its mean, right? And the standard deviation means that how far are they away from this mean. So if your standard deviation is high, it means that this value is quite far away from your mean. Just like your mean is 5 and you got the value is 7, so the standard deviation could be 2. And the variance is you double this standard deviation, like your standard is 2 and your variance is 4. And the Levine test is compared two groups variance, like the female and male, and they want to know whether there is a difference between their variance. So if the variance is quite similar, so is that equal? It means that they have a same trend of the normal distribution. So it means that the shape of their Bell wave is quite similar. Does that make sense? And if they are similar, then you can do the t-test to know whether the difference between these two groups, they have a same trend, but there is always something different in their lines. I think I have explained. Could you get it?
Yes, no? Do you guys want us to try to explain it one more time differently?
I'm not quite there yet, I don't think.
Okay, that's fine. So basically, okay, we have two different genders. To be able to compare them properly, it would be really stupid if, let's say, we can't really compare if all men are on one side of the curve and then women are properly distributed, right? To be able to compare the two genders properly, it would make sense to make sure that the way they're distributed in your normal distribution is relatively similar. Otherwise, it's like I'm comparing, I'm trying to make it into an easier example. I don't know, let's take, I'm a relatively short person, and then there's a really tall person. You can't really compare me to them because we're two different, like different heights of people. Or let's say, no, let me make it simpler. You can't compare how a dress looks on me versus how a dress looks on a taller person because we're completely different height. that's kind of what the Levine test aims to do. It aims to make sure that the two things that we're comparing are relatively similar in the distribution.
I have a question. Is it that when you say that they're relatively similar, do you mean as in like how high they would be against each other, or like where they fall?
Just that the
No,
curve
go ahead.
is relatively, so the curve shouldn't be normally distributed for one and then tighter for others. It should be distributed and varied relatively the same way.
Okay.
I think it's just like you want to test two groups of people who have some same features, but no, no. You want to test two group people with same features, but their ideas are different.
Is everyone good, or do we try one more explanation?
Actually, you don't. I think we don't need to understand how the Levine test works. You just need to know if the value is equal.
Right.
So the first line, then you can use the t-test. It has some meanings. But if it's not equal, then the test is meaningless.
Yeah, basically, you guys don't really need to understand what the Levine test does, but it was bothering me a lot that I didn't understand it. So I'm just trying to explain it to you guys. But you just really need to know what the number under the Levine test tells you or not. That's all you really need to know. Okay, so I think I remember Martin saying, one second, let me open his thing again about the Levine's test. Okay, yeah, so we also need Levine's test to be above 0.05 for the equal variances to be assumed, which is what generally we need to do. So actually, we just need to know if the variances are assumed or not in order to know what row to look at for our test. So in this case, can you guys all see my slide with the table and the little squares down there? Okay, yeah. Great. So in our case, so usually when you get this output, the first thing you need to look at is the Levine's test to see if equal variances are assumed or not. So you look at this number, the 0.54. Because it's above 0.05, equal variances are assumed. Yes? It literally just says it there in the table. Let me get my annotation tool again. Hello. Okay, so there's these two, this and this. So you look at the Levine's test. If it's above 0.05, it means that this is correct, that equal variance is assumed. And in that case, you would look at completely just this row. Okay, if the Levine test is lower than 0.05, you would have to look at the other row and read it. So because ours is, it shows that equal variances are assumed, we're gonna look at this, okay? And the value is 0.25. Now, what the hell does that mean? Let me see.
So actually this value is similar. You can think this similar as the chi-square test or the normal distribution. So if the significance is higher than 0.05,
okay,
it means you need to you can't say you reject your non-hypothesis, and In this Levine test, the null hypothesis is the variance is equal. So it is higher than 0.05, then it's assumed that it's equal variances.
Okay, and then so when you look at your t-test number, it's higher than 0.05. So it means that it's not significant, which means that there is no difference between the two. Yeah, so it's kind of similar to the chi-square, wherein we needed it to be less than 0.05 to be significant. So you also need the t-test to be less than 0.05 to be significant. If it's not, then it's not significant, and it means that there is no difference between the quantity of coffee that husbands have and that wives drink. Okay, so this is the way it's reported. I switched the slide, and it shows that these are the values that you need to input, and this is the stuff that you need to say. Okay.
So we don't want difference on the t-test. We want them to be similar.
I mean, yeah, theoretically, if you're trying to prove that they're similar, you would want them to be similar. But unfortunately, you conducted your entire research, and it turns out it was useless.
Oh, okay. But yeah, so that's what we're looking for when we're looking for that 0. So if you go back, could you go back to the table, please?
Yeah.
So you want it on that top row rather than the bottom row.
We're on the top
So if
row.
it's on the top row,
Yeah.
that means that your two variables are like similar.
Yes.
Yeah. Or the results from those variables are similar. But if it was below that, then you would have failed to have proven your hypothesis.
So if the result is on the first row, and
yeah,
then the t-test should be useful. It have some meanings, but if it is on the second row, then the t-test is in some degrees kind of meaningless.
okay.
So you need to use this on the first row.
But
great, thank you.
Ethan, at the end of the day, you can have equal variances assumed, but have a failed t-test. Because, I mean, the first step is having equal variance. It actually doesn't even matter if it's equal variances or not. It's fine. You just need to know if they're equal or not, just to know which row to look at. The equal variances cannot be assumed, and you can still look at the t-test. You just need to know what row to look at, but the part that tells you whether or not there's a significant difference between the two genders is the t-test. It's the 0.245. So you just need to look at the Levine just to know which t-test to look at value. Yeah?
Right. So I look at the one, so it'll only be on equal variances assured or equal variances not assured.
Mm.
And I go to the one it is on, and I go across to that sig,
Yeah.
whatever that says.
Yeah.
And I read the one that's there, yeah?
Yeah.
Nice, thank you.
Of course. I'm gonna go through Martin's example anyways as well. More examples, the better. Let me find it. Okay, that's the independent. Let me stop sharing and then reshare. Okay. So in Martin's example, we want to test if males and females differ in their attitude towards online grocery shopping. Okay, okay, we do this SPSS, it's fine, whatever, we'll go through that later. And this is the result we get again. Okay, so again, we have this is it, our Levine's test for equality of variances. Okay, it's 0.456. it's above 0.5, 0.05, so equal variances are assumed. Okay, so we look at the first row. Then here it says, this is our t-test value, it's 0.026. Is it lower or higher than 0.05? It's lower than 0.05. And that's what we need for it to be significant. Right? Or is everyone lost?
I understand that. My problem is it's the decimals that get me. Like I thought 0.05
Was higher.
Yeah, so I thought it was higher than 0.05. Is that right? No,
Okay,
that's
yeah.
wrong.
No, I get you. It is confusing. It takes me some time too, but it's fine. So just do the math in your head, and then you'll notice that it does work. It is significant. And so what does that mean? Hang on, what does it mean? So our t-test is significant. What does that mean for our research?
So if it is significant.
No, actually, don't answer. Don't answer. I want them to answer.
Oh yeah.
You're such a stern teacher. You're gonna hit me with a ruler as well.
Wait, does it mean that that it's equally wait, I forgot how you were explaining it. It was the thing that you were explaining before that I wasn't getting, that it was equally.
No, that's the Levine part. We already got through that. We saw that equal variances are assumed, and then we got to the part where we have to see the value for our t-test, and we saw that it's smaller than 0.05.
Right.
Which means that it's significant.
That means that oh yes, the significant and insignificant thing.
Yes, but what does significant mean?
Doesn't that prove your hypothesis? Like it's correct?
Yes. Go ahead, keep going.
Oh, I mean, I think I'm going along that line because, yeah, I would think that benchmark fudge. Okay, the 0.5 proves that. Okay, I lost my train of thought. I mean, that's what I would think. It has nothing to do with your null hypothesis, right?
Right. Yes, okay, but in terms of what is our research? Our research is, do male and female students differ in their attitude towards grocery shopping?
Yes.
Does it mean that it's not related?
No, it does mean that there is a difference.
Like, I'm on the right lane, right?
No, Mia, you're right. Yeah. It means that the difference between males and females online shopping grocery attitudes are significant.
Okay.
Did everyone get that?
Yeah, I get it now.
And the thing is that their behavior is not related, it's different.
So basically the 0.5, that's the benchmark we have to follow from Martin, and that determines whether the hypothesis is significant. Because if it's higher, that means that hypothesis is shit. So does that make sense, Suel?
Yeah.
Okay.
So the difference between the independent variables is significant.
Yeah.
That was a question, sorry.
Yeah.
I can see the disappointment in Yara's face.
No, I'm not disappointed. Look, I'm happy that at least you understand now. That's all I care about. And so this is the way you'd, oh yeah, I can move this. Hang on, I just figured out that I can move you guys and put you down there, put your
I just
faces
wish
down
Martin could just say that straightforwardly in his lecture.
there. Okay, so this is the way you would report it. Okay, so you report the average for both. We find that on average, males' attitude towards online grocery shopping is lower than one of females. So we got that because of the mean for both. So the mean for the attitudes, let me go back here. These are the means for males and females. So the mean for the men was lower than the one for women in regards to their attitudes to grocery shopping. So you say that on average, males' attitude toward online grocery is lower than one of females, and you put the means in parentheses to prove that this is how you understood that. And then you say the assumption of homogeneity of variances was not violated, which is our Levine's test. Okay, because we got equal variances assumed, you say that the homogeneity of variances was not violated. And we find that the difference between males and females was significant. Yeah. Okay, great. I'm just trying to figure out, Ashley, I don't know if you can answer my question, because in the report, he says, the assumption of homogeneity of variances was not violated. If it's violated, what happens?
If the variance is violated, it means that, make a simple example, there's a group of female and a group of men, and their ideas about online shopping are totally different. There is no same way, just like the whole group thinks this online shopping is useless, and the other group thinks the online shopping is quite useful. So from the first step, what they think are quite different, then we cannot compare them from the t-test. For the t-test is to test a group with some same features, and they may have some small difference between their ideas, like just to test the mean, right? The mean of men, I forgot number, but if the mean of men is 5 and mean of women is 4, then we test the 4 and 5 difference, but we cannot compare like 7 and 1, right? It's quite different. So if it is quite violated, then the next result is in some degrees meaningless.
Okay, so in that case, the t-test would be completely meaningless, and we don't really do anything with it?
It's not completely meaningless, but you can still use this number, but it's not quite credible.
Okay, I see.
At the first step, these two groups are quite different.
Okay, I see, I understand. Thank you. Okay, next, I'm gonna go back to my other slide. And we're gonna go through, I think, oh shoot, there's no other example. Okay, I guess we're gonna stick to Martin's. Boo. Okay, that's fine. We're gonna stick to Martin's example now. Okay, so let me go back, because before that there was the one sample t-test. Okay, so in Martin's example for one sample t-test, this was our hypothesis. The mean of consumers rating online shopping as useful is larger than 4. So in a one sample t-test, you already have an idea of what your result is going to be. You know that the average is larger than 4, and you want to prove that. So because you know that, a one sample t-test would work because you only need to prove one side of the curve. Okay. So you do the SPSS thing. Oh, do you guys want me to go through SPSS for the independent samples t-test before we do the one sample t-test?
Yeah, we're doing that tomorrow, aren't we?
Probably, yeah. Okay. I think I have my output. Yes, it's. Oh, you guys can't see my SPSS. Hang on. Okay. So I have everything recoded still, I think. So we're just going to use it. So in this case, in the independent sample t-test where we were testing the attitude towards online grocery shopping, 2 questions in our survey tested that, which were 4.1 and 4.2, which I think are, let me open the label. Overall, online grocery shopping is very easy to use to very difficult to use, and overall, online grocery shopping is not at all useful and extremely useful. So these 2 both test the attitude towards online grocery shopping. So we need to combine both of them into one in order to be able to test our hypothesis. So I'm pretty sure I did that already. This is it. This is attitude. I had already recoded it, but so that you guys can do it, what Martin did, I think, is the following. Oh, first of all, right, these are coded differently. So 4.1 is coded from positive to negative, and 4.2 was coded from negative to positive. So in order to sum them up, we need to recode them. So I hope you guys remember how we did that before. Does anyone remember how to recode a variable?
It's recode into different variables, isn't it?
Yes. And then you input it, and then you name it differently, right? And then you go into the old and new values and you switch them around. Okay, so I'm not going to do that since I already have it recoded here. And then you need to create your new variable that sums them both up. So to do that, you have to go into compute variable. And so you call it, I'm not going to do it, I'm just showing you guys. So you call it attitude. And then you need to sum them up. But we don't want to sum them up together. We don't want to have all the variables mixed up. We just want to add up the average of both. So what you're going to do is, where are they? You go to, sorry, the new one plus the old one, plus the other one. And you divide them by 2 because we want the average, right? And then you just click OK, and you get your new variable. Okay, and that way you have this new variable called attitude. Okay, and then now, since everything is properly organized and everything's the same, we can go and actually test, do the t-test. So we go into analyze, compare means, and we go into independent samples t-test. Okay, so usually for every t-test, you just do this. You can see there's the one sample, the independent sample, and the pair samples. So you click on here, and I think, I don't remember which one was the grouping variable and which one was, okay, the test, sorry, hang on. The test variable, I think, is the attitude. That's the one we're testing. And the grouping variable would be the recoded, no, not the recoded, the other one. Where is it? The demographic, we're doing male and female, so gender. Okay, but now we need to define the group so that SPSS knows how many groups we have. So we just have male and female, so we have 1, and 2. That's it. And then you click continue. I don't think we did bootstrapping. He went through bootstrapping very quickly, but he said we don't need to do it, so I'm not going to do it for you guys. And then you click OK. Can you guys see my output, or can you not?
No, we can't see the output.
I hate this share screening. Let me go to the output. And then this is what you get. So we have our mean here for the male and female, right? And then we have our entire table for the t-test. So you have your Levine's test here, where you need to see if equal variances are assumed. They're assumed. So you look at this. This is your t-test value, and that's it. Yes, all good? Does anyone want me to go through the steps to get here again, or is it okay? Okay, great. We will go back to this, okay? And we're gonna go back to one sample t-test. Okay, so for this one sample t-test, our hypothesis is the mean of consumers rating online shopping as useful is larger than 4 on a 7-point scale. So again, in a one sample t-test, you come in with a number, with something specific that you want to prove. And because that's why you use a one sample t-test, because all you need is one side of the curve. You just need to prove one side of the curve. You don't need a two-tailed thing to prove it. So, okay, forget this. This is math. So this is the output you would get with a one sample t-test, and this is our t-test value, 0.000. Is this lower than 0.05? Yes, okay, great. What does that mean?
That's significant.
Perfect, it's significant, excellent.
Oh my fuck.
What does that, and more, what does that mean? I mean, the result is right there, so I'm not gonna ask you guys. It's significant, which means that the mean is much higher or significantly different from 4, which is our hypothesis was that the average is higher than 4. So because of the result we got, we can say that the average is significantly different than 4, and thus Sainsbury's should definitely double their investment in online shopping. Make sense? Okay, now I'm going to go through just how to get it on SPSS. It's very simple. Let me stop sharing and then share again. I'm just going to do it from here. It makes it easier. Okay, so you go again into Analyze, Compare Means, one sample t-test, and you put your data. Shoot, which one is it? Is it very easy or useful? Okay, useful, I think it's this one. Yes, so you put it in there. I don't think we need to put anything else. And you just click OK, and then you get it.
And the test value?
Oh, do we need to put a test value? Hang on.
Yeah, because your test value is 4.
Oh, right, yes. Sorry, yes, that's important. 4 is because that's what your hypothesis said, that it's 4. So you need to put that so that it tested against 4. And then the only thing it does is that it shows you here the test value equals 4, because I think I got the exact same table. It's the exact same table. The only difference was here. Test value equals 0, and here test value equals to 4. And that's it for the one sample t-test.
I think your mean difference changed as well.
Oh, did
with
it?
the, I think.
Oh, you're right. Absolutely, yes. Oh, yes, there's an extra 4. How interesting. Okay, thank you for pointing that out. Okay. Okay, the last one is the paired sample t-test. So I think I'm going to go through this with you guys and understand it along with everyone as I explain it. Okay, so this is our question. Do consumers consider price discounts more important than a low price when it comes to online shopping? Okay, so I'm just going to look at the 2 different questions that he said we need to analyze. So he said we need to analyze question 3.1, which is please rate how important price is as a factor when you decide. Stop share and start share. Okay, so for this question, we're using this question. Please rate how important price is as a factor when you decide to purchase your groceries online. And this one. Please rate how important online discounts are as a factor when you decide to purchase your groceries online. So we're comparing price discounts and low price. Oh, okay, so I guess that's why it's a paired sample. It's the same group of people, right? But we're testing 2 different things. We're testing low price and price discounts to figure out which is more important. So that's why it's a paired sample t-test. Okay, that makes sense to me. Does it make sense to everyone? Okay. Okay, yeah, so this is where we need to check again for normal distribution. And so you do that by doing the histogram and making sure that the bell curve looks normal, and it does. Martin's file shows that it does. And okay, so okay, actually I'm gonna go through SPSS with you guys now, and then we'll analyze the results that we get. Okay, so we're gonna go into analyze again, compare means, paired samples t-test. Okay, and then we have to put both our variables. So that would be this one. Yes, I know. Okay, and then this one. Okay. Oh, that's where he did the bootstrapping. It's fine. I'm not gonna do it. So let's just see the results we get. Ashley, is there anything other than bootstrap? Is there anything else I need to fix?
He used a bootstrap to make the result more credible, but
oh, that's true. Right.
Yeah, but distribution already is the normal distribution. So
yeah,
actually you don't need to do the bootstrap.
Okay. Yeah, if I remember correctly, bootstrapping was mainly like taking it on a larger scale, right? So if you don't have the like a good number of respondents, if you have, let's say 20 and you were aiming for more, you would do the thing called bootstrap, because SPSS would somehow kind of replicate and give you a larger number of respondents to analyze everything. But
yeah, there is a theory in statistics is that if the number is over 30, then we can use a normal distribution to analyze this sample. Yeah, so the bootstrap will make this sample more similar to a normal distribution.
Okay.
Yeah.
Okay. So, but you guys don't have to worry about that. We really don't need it. So I'm not gonna do it now. So I think you just click OK, and then you get. Let me just close everything else so I don't get lost. Okay, that's it. Okay, so these are the different tables that we're gonna get. So this is.
Sorry, you need to show us the output.
Ah, shoot. Yes. Okay. Actually, I'm just going to share Martin's then. Okay, so these are the results that we're supposed to get. Okay, I got one more extra table that he didn't get. But I guess that's okay. Oh no, that's it. That's the same. Oh, hang on. Okay, Ashley, in his table he had in his table he has the standard deviation, and I don't have it in mine.
Oh, let me check mine. Let me
You
see.
know why?
Yeah.
Is it
Mine's
just because
missing a lot of that information.
mine doesn't look like his at all? I'm a bit worried. I have no clue what I did wrong.
Is that the bootstrap thing?
I don't know if
I
it's
thought
because
the
of the
thing here. I think it's because he did a bootstrap.
I guess.
So if you use the bootstrap, then you will get the mean and standard deviation and this here.
Oh, actually, I do have the mean and the standard deviation, but I don't have them the way he does. But they're the same values, so I'm going to assume I didn't do anything wrong.
Yeah, for he has done the bootstrap.
Yeah.
So the data is kind of different.
Okay, is it because I don't have those two columns that say 95% confidence interval? I don't have them.
Yeah, this one is used for the bootstrap.
Okay, great. Okay, so I guess we just have to look at that red square that we should all get anyways if without the bootstrapping. This is what I got. So it has the mean and it has a standard deviation for both questions. Okay, and then in the other table, there's, okay, the mean standard deviation, and then there's the T and the degree of freedom. Okay, oops, sorry. Okay. I'm just trying to figure out what it is I'm supposed to be looking at. Oh, I think we're supposed to just look at again at that thing, the 0.17. I think this. I think that's what we need to look at. But it's lower than 0.05, which means that it's significant. But what does that mean though? 1 second. Important than a low price. I guess it means it's significant, and that means customers do consider something more important than something.
Yeah, you're right, Yara.
Am I? I'm just looking at the reporting.
So I think it means that customers find online discounts more important than they do price.
Yeah, it's right.
Yes, you're right, because
So-
the mean for online discount is higher than the one for low price. You're right, Ethan.
Yeah. Wow, I worked that out.
Honestly, I can't. I'm so proud. I feel like a mom whose son just achieved everything. Okay, I'm just looking at the reporting.
Okay, so that's because there's the significance. It is significant, the difference.
Yeah.
And so I look, and so the one that has the higher mean is the more important to customers, and the one with the higher mean is the online discounts.
Yeah. Okay.
Great.
Excellent. Okay, so let's look at the way you reported it. When comparing if price or promotion is more important, we find that price received a mean rating of 5.14, whereas online discounts received a mean rating of 5.57. Using a paired sample C-test, we found this difference is negative 0.43 is significant. Where is the negative 0.43 though? Where did he see that? Oh, it's this, I think. It's this, if everyone sees where I'm pointing at. Mean of, so he rounded it up at negative 0.43. So we found that this difference is significant because of the t-test being smaller than 0.05. Supporting our hypothesis that price promotion plays a more decisive role than a low price in general as a driver for online shopping. Okay, and then he explains why he did bootstrapping. And that's it. Okay, so Ethan was very on point with his interpretation of our results. Okay, and then we did this, and we didn't do this yet. So that ends it for our session today, you guys.
Thank you to both
Does
of you.
anyone have any questions at all, or does everyone understand absolutely everything right now about these tests?
I understand it a lot better than I did from Martin.
Okay, good.
Yeah. I think I just need to go back over everything and try it on my own, and then I'll see clearer from there.
Okay, does anyone have any more questions?
Or do you need a summary of these tests?
Yes, Zizi, sure, of course. Go through them again and ask me whatever questions you have. Okay, I'm gonna stop the recording now then, I guess.